Welcome back, and this is lecture 27. So in the previous lecture we were looking into how to use PMOS in place of a resistor, and we came up with an architecture where it seemed like we should be able to replace a resistor with a PMOS transistor and get high gain in a common source amplifier, right? So before proceeding with the same thing, let's have a quick recap on the differences between an NMOS transistor and the PMOS transistor's characteristics, right? So that will be useful in the long run. So this is a PMOS transistor, this is an NMOS transistor, and this is a PMOS transistor. So the arrow always indicates the source terminal. So this is drain, this is source, this is gate, this is source, this is gate, this is drain. Very often you will see that another symbol is used to refer to the PMOS and the NMOS, and that symbol is the following, without the arrow. This is under the understanding that we know that this is a gate, but we don't know which side is the drain or the source, right? So this happens quite often if the voltages or the terminals of drain and source can flip, right? One side can be higher, other side can be lower. We really don't know which is drain and source. It completely depends on what the application is, or which side is the higher voltage, right, or which side is the lower voltage. Hence sometimes you will see that that symbols are expressed without the arrow, with the understanding that as a user or as a designer we know which side will be the source or the drain. Similarly, in case of a PMOS, the similar symbol is the following. We have a bubble at the gate, right? We have a bubble at the gate, and we have terminals without the arrow, again with the understanding that if we know which is the higher terminal, we will ascribe that terminal to source, and the lower voltage terminal will be ascribed as the drain, right? So since we are dealing with PMOSs and NMOSs, I thought you should be aware of this of these symbolic differences also. Okay, so quick recap. In saturation, IDS for NMOS is half mu n Cox W over L VGS minus VTN whole squared. In case of a PMOS, ISD is equal to half mu P Cox W over L VSG minus mod of VTP whole squared. If I have to include channel length modulation, then this becomes 1 plus lambda n VDS, then this becomes into 1 plus lambda P DSD, right? Okay, so what is the expression, what is the condition for what is the saturation region condition? The saturation region condition for, or rather what is the on condition in case of a NMOS? The on condition is, so let me say this is the on condition. On condition for the NMOS is VGS has to be greater than equal to threshold voltage, VTN in this case, because we have been expressing it like that. Okay, so what is the on condition in case of a PMOS? On condition is VSG should be greater than equal to modulus of VTP, right? Again, note that in most cases VTP is a negative quantity, but in that case we refer to VTP with respect to VGS, but since we are referring with respect to VSG, we are more interested in the mod of VTP, because dealing with negative quantities can be sometimes lead to some confusion in terms of which side the current directions are, right? Okay, so what is the condition on saturation region? Saturation region condition is VDS should be greater than VGS minus threshold voltage, which implies the drain voltage should be greater than the gate voltage minus threshold voltage. This is the condition that we were using throughout the course. So what is the corresponding condition in case of a PMOS? The corresponding condition is if we simply say that everything is reversed, right? Source becomes drain, drain becomes source, and so on. So if we just use that, that understanding, we should write it as VSD should be greater than equal to VSD should be equal to VSG minus mod of VTP, VTP, okay, which essentially means that Vs minus Vd should be greater than Vs minus Vg minus mod of VTP, right? Which means this goes off, which means Vd should be less than equal to Vg plus mod of Vt, right? So this becomes the saturation region condition. In plain English, the saturation region condition for an NMOS is Vd can go one threshold voltage below gate, right? So this is a minima condition of, so this is a Vd minimum can go one threshold voltage below gate. In case of a PMOS, this will be Vd has to be less than something, which means this is the condition of Vd maximum, right? So in case of this, this is Vd max can go one threshold voltage above the gate voltage. Okay. Then what else? What are the small signal parameters? The small signal parameters in case of NMOS is Gm is equal to, mu n Cox W over L VGS minus VTN. In this case, in the case of PMOS, it will be Gm is equal to mu P Cox W over L PSG minus mod of VTP, right? Similarly, you can write in terms of current, where under root current term will come. Similarly, GDS is lambda n IDS. Here GDS will be lambda P ISD, because the current of ISD is positive. Okay. What is the final thing that we should see? The final thing that we should see is a small signal model. The small signal model we discussed that both the small signal models are identical, but we choose to draw it in a slightly different manner because ultimately we know that the drain in case of a NMOS is on top, and the drain in case of a PMOS is generally on the bottom, because drain is at a lower potential, right? In a quiescent condition, right? Not necessarily in the incremental condition. So this is gate, this is drain, this is source, and this is Gm times VGS, and this is GDS in case of a NMOS. So in case of a PMOS, we have again the gate remains gate, but we call the top terminal source and the bottom terminal drain. This is GDS. Again, this current we will call as GM VGS, but now since the incrementally both are same, the current has to go from drain to source, just like in the circuit in the left. So the arrow points upwards, right? Okay, so that is as far as we need to know about the PMOS equivalent with respect to NMOS. And now we will treat it as almost the in terms of the incremental equivalent. It's basically the brother of NMOS, right? Right, with one critical difference. The only critical difference is the lower terminal, the lower voltage terminal is a drain voltage. Okay, fine. And obviously there is another critical difference, and that is the on condition here is VSG has to be greater than VTP, right? So these two, if you keep these two in mind, then we are good to go. Okay, so what was it that what was the circuit that we were discussing when we stopped in the previous lecture? The circuit we were discussing was we were having a common source amplifier, right? And this was biased using, okay, so hold on, we had a common source amplifier. This was biased using a current mirror, right? And because this was biased using a current mirror and we wanted to feed the input, so we had to uncouple, we had to ensure that the input is AC coupled. So this is RC, this is the RS, this is the RC, this is C infinity, or we can call this C1 or C infinity, it really doesn't matter. Okay, so this we have already done a long time back in this course. The only difference here was, instead of putting this RL here, we would have liked to put a PMOS transistor, right? So this was VDD, but this PMOS transistor needed to be biased for the same current I0, right? For the same current I0. And how did we bias? We saw that we basically will be using the biasing scheme of this structure to bias the NMOS, bias the PMOS for a current of I0. So we use the same current mirror based bias, and we put I0 here, right? So let's name them. Let's say this is called this M1, this is M2, let's call this M3, M4. Okay, and this becomes our V0. Okay, so again, note that this doesn't really ensure that both M1 and M2 is in saturation. If we assume that they are in saturation, then this combination of M1 and M2 is essentially our common source amplifier, right? So I had asked you to sketch the small signal equivalent of this and figure out what will be V0 over Vi. I hope you have done that. Let me quickly run you through what needs to be done, right? So all we need to do is replace all the transistors with their incremental equivalent. So let's do that. Let's start with M1. If I neglect the GDS, then life becomes slightly easier, and let's do that for the time being, and then we'll introduce GDS later. So M1 has a gate, right? And this is M3. These are grounded, right? What is the M3 is driven by current source. The current source opens up, but the gate of the M3 is connected to the drain of M3. So incrementally this becomes that. So this is gate, this is drain, right? Now what happens to, what can you replace this? What is the impedance looking into this terminal? The gate drain connected terminal. We have done this before. The impedance looking in is 1 over GM, right? So we can replace this entire structure with 1 over GM. 1 over GM to ground, right? So you have an RC here, okay? Then this capacitor, this is RS, this is VI, okay? And if we size the capacitor in such a way that it is like short circuit at the signal frequency, and if we size RC in such a way that RC is much greater than RS, right? So if C1 tends to infinity, and RC plus 1 over GM is much greater than RS, then what can we do? We basically then we can infer that this guy does not load Vi, so that contraption gives you effectively infinite impedance. So, and C is a short circuit, which means this voltage here is approximately Vi. If that is Vi, I can remove all this stuff, right? I can remove all this stuff, and I can assume that this voltage is, the gate voltage of M1 is Vi. So this current becomes GM1 times Vi. Okay. So M3 basically goes out of the picture. So let's go on the top and concentrate on what's going to happen with M2. So what's going to happen with M2? So what will you do? We'll replace the incremental equivalent of a PMOS. What is the incremental equivalent of a PMOS? Right? Incremental equivalent structure of a PMOS is this guy. Okay. So we'll basically replace that. So let's do that. So this is the drain, this is the source, this is GM VGS moving upwards, right? And this is the gate, and this drain and this drain are connected together, and let me mark it as GM2, right? GM2 VGS. Okay, instead of saying VGS all the time, let me call this VG2. So this becomes, so this terminal is VG2. So this is GM2 times VG2 minus VS. What is VS? Incrementally, what is VS? S is connected to VDD. VDD is short circuit, so incrementally source is shorted. Correct? So this becomes GM2 times VG2, right? We don't have to bother about the source terminal, right? So this is like the bottom terminal. I mean, this is like the case with M1 also, right? Okay, fine. What is happening with M4? So this is anyway shorted, right? So same thing. Let's replace our stuff with. So this is, we have a current source here. So current source opens up. This is the drain voltage. The drain and the gate are connected together. The drain and the gate are connected together, and this is GM3 or GM4 VG2, right? GM VGS or GM4 VG2, correct? Okay, great. So can we simplify this contraption? Can we simplify this contraption? What is the impedance looking in? What is the impedance looking into the gate of this guy? What is the impedance looking in gate of M4? Because the gate and the drain are connected, this again is a diode connected transistor equivalent to that of an NMOS transistor, right? So what happens in a diode connected transistor? What is the impedance looking into the gate of a diode connected transistor, the gate or the drain? In case of an NMOS, it's 1 over GM. So in case of a PMOS also, it will be 1 over GM. You can actually, I will encourage you to do it yourself once, right? So use the PMOS transistor, use the M4 configuration, diode connected configuration, and find out what is the input impedance, right? So I made the statement, but you should once verify it yourself. So this becomes a diode connected transistor. This becomes a diode connected transistor connected to the ground, which is 1 over GM4, right? What is the current into this terminal? The current is 0. If this terminal current is 0, what is this voltage? VG2. VG2 is also 0, right? Fine. So what is left? So we have neglected the GDS, right? We have neglected the GDS. Let's put the GDS of M1 back, right? So let's put GDS of M1 back here. So this is GDS1. What about this guy? So this is GDS2. So let me just say that there is a ground here, so that I don't have to sketch the I don't have to connect the ground all the way from top to bottom every time, right? So if we had considered the GDS of M4 and M3 also, would it have caused any difference? No, right? So if we had considered the GDS of M4, instead of 1 over GM4, the resistance would have been 1 over GM4 plus GDS4. But in the end, VG2 would have been 0, right? Okay, great. If VG2 is equal to 0, what is its impact? What is the impact of VG2 if it's 0? If VG2 is equal to 0, this VG2 is 0, which means this current source goes off. Correct? If that current source goes off, what is the simplified circuit? What is the simplified, how can we simplify this circuit further? This is what we should get. We have this VI, right? This is GM1 times VI. This is GDS1, and we have GDS2, right? And this is also grounded, and this is V0, right? Everything else went off, right? This is the beauty of analog circuits. This is the beauty of approximations, right? So once you know how to look at how to simplify a circuit, then everything becomes very simple. And we know, we have seen this architecture multiple times. What is V0 over Vi? V0 over Vi in this case is minus GM1 times GDS1 plus GDS2, right? Okay. So if we had neglected channel length modulation in this case, right? If we had neglected channel length modulation in this case, the GDS1 and GDS2 would have been 0, and we would have got an infinite gain. Now that would have been infinitely wrong, because I mean, I cannot neglect a finite thing with respect to infinite, right? Because I cannot neglect a finite thing with respect to infinite, I have to consider channel length modulation. However, if instead of GDS2, if we had a resistance RL, and the resistance would have been the value of the resistance would have been much smaller with respect to the RDS of the transistor, then I could have neglected the channel length modulation, right? So as you might have, as you should remember is, that it's all horses for courses, right? For whichever condition we can make the approximation, we should be able to make that approximation, but you should be mindful of the fact that that approximation will not hold good under all conditions, right? So that knowledge of that condition is extremely important. Okay, fine. So this is what it is. Now if I have to find out, for example, the swing limits, right, for this particular architecture, so what should we do? So let's do that also. So let me copy this guy. Okay, so now you see there are like 4 transistors, so we'll have to find out the condition of linearity and saturation condition and cutoff condition for all 4 transistors, right? So let's start off with the condition on M1. So I will do for couple, then you can do the others. So let's do the condition for M1, right? So what will be the condition for M1? For this, we need to we have to assume something, right? We have to assume something, and let's assume that V0 has some quiescent voltage to start off. Again, I haven't told you what is the quiescent voltage of V0, right? So let's assume that so this will generally be given, or the circuit will have some additional contraption through which you will be able to estimate what the V0 voltage will be. So let's assume for this particular case, note that don't assume this particular thing that I am going to assume in a generic case. For this particular case, assume V0 quiescent to be VDD by 2, right? I just picked something out of the hat. let's say this is being said by some other circuit which is connected across it. Okay, so let's assume V naught Q is VDD by 2 and let's proceed, right? So for M1, what will be the condition? M1, what is the set limit? So this is easy. So if we assume that the no loading and everything, then this voltage is approximately Vi, I mean this quiescent plus Vi. So what is Vg? Vg is VGQ1 plus Vi. What is Vd? Vd is VOQ, which is VDD over 2 minus gain, right? Minus the swing, this V naught, correct? What is V naught? V naught is the gain of the amplifier times Vi. So this becomes VDD. So this becomes VDD by 2 minus GM1 by GDS1 plus GDS2 times Vi. So what will be the condition? The condition for saturation will be Vd should be greater than equal to Vg minus threshold voltage N, and you can plug in the values and you will get something, right? Similarly, you will get the same thing for something for the cutoff condition also. But I would like to concentrate more on what's happening with the NMOS transistor, because that is the new thing in our system, right? Okay, so let's do that. Right, so we know that this quiescent current is IDSQ, right? IDSQ is equal to how? What? IDSQ is equal to I naught, because we have a current mirror which is setting into I naught. Okay. So what will be the condition for this? Is M2. So what is this? This is the IDSQ current which is equal to I naught. What is the incremental current? What is the incremental current that is flow? What is the incremental current that is flowing? What is the, how will you find out the incremental current? To find out incremental current, we have to go back to our incremental picture, right? So what is the incremental current that is flowing? It is GM1 times Vi, right? GM1 times Vi is flowing into the incremental load. Correct? So since GM1 times Vi is the incremental current, so this total current is I naught plus GM1 times Vi. Okay, right? What is this voltage? What is the total voltage? This is V naught, right? What is the total voltage? Total voltage is V naught over 2, sorry, VDD over 2 plus V naught. What is V naught? Which is minus GM1 by GDS1 plus GDS2 times Vi. Correct? This is the total V naught. Okay. So do you think, okay, so let me ask you one question. Where is this GM1 times Vi, incremental GM1 times Vi going? This incremental GM1 times Vi is going into the modeled resistances, right? The incremental resistances. What is meant by model resistances? What is the genesis of those modeled incremental resistances? The genesis of that is when this drain voltage swings, when the drain voltage of an NMOS or a PMOS transistor swings, the drain current also changes by slight amount because of the channel length modulation, right? It is when we say that this incremental current is going into an incremental resistance, what we are essentially saying is that there will be a slight change in the drain current, right? And what we essentially are trying to model, what we are essentially trying to say is, we'll assume the transistor is ideal, but in parallel to the transistor there is an incremental resistance, right? And so the incremental current is then going into the incremental resistance, right? But as far as the quiescent current is concerned, as far as if we neglect channel length modulation, for example, is the current through M2 changing? The current through M2 isn't changing because this is a constant current bias, right? So the VSG, the VGS of this transistor or VSG of this transistor is fixed. What is the VSG of the transistor? VSG of the transistor is threshold voltage mod of threshold voltage plus overdrive, and overdrive is that under root 2 I naught by mu C ox W over L and so on, right? So for all practical purposes I can say that this I naught is kind of constant. So if I naught is constant, right, then will M2 ever go into cutoff? When can M2 go into cutoff? M2 can go into cutoff only when V overdrive changes, right? If the transistor VSG goes towards 0, the M2 can go into cutoff. But since its V overdrive is not changing, right, it's fixed, M2 cannot ever go into cutoff, right? So M2 is always on. So the cutoff condition for M2 is no longer valid, right? What about the saturation condition? So cutoff condition invalid, right? So what is the saturation condition? The saturation condition will be our drain voltage, that is V naught, right? So let me write in terms of VD, right? So VD, there should be a maxima condition on VD, right? So which means VD should be less than equal to the gate voltage, the total gate voltage plus the threshold voltage, right? What is VD? VD is VDD over 2 minus GM1 by GDS1 plus GDS2 times VI. This should be less than equal to, what is VG? VG is VDD minus threshold voltage plus V overdrive, right, plus mod of VT, right? Right. So this is the maximum. I mean the condition that we will arrive after solving this algebra will give you the swing limit that you have to honor for as far as M2 is concerned, right? Okay. So before we end this lecture, what I would like to draw your attention to is that since it looks like an NMOS and PMOS transistors are siblings, right? They're brothers and sisters, right? So which essentially means that whatever the NMOS transistor can do, a PMOS transistor should also be able to do. I mean, as it turns out, we started the course with an NMOS transistor, but that did not necessarily be the case. We could have as well started with a PMOS transistor, which means all the amplifier configurations, right? Common source, common gate, common drain, VCVS, VCCS, CCVS, and everything that we have done with an NMOS transistor can also be made with a PMOS transistor, right? So let's see quickly what I mean by that. So we have this so let me so this is the common source amplifier configuration with an NMOS transistor, right? What will be if I have to make a common source common source amplifier configuration using a PMOS transistor, what should I do? I should basically replace the NMOS with the PMOS first and with the source at the higher voltage, right? Here the source is fixed voltage. What is the fixed voltage? The fixed voltage is ground. Because the source is the lower terminal, it has to be grounded, right? Fixed voltage is a lower terminal voltage, which is ground in case of a In case of a PMOS transistor, it should be the higher terminal voltage. So this becomes a PMOS transistor. The incremental grounded terminal will be that will be the source, which is VDD. At the drain, we connect RL. Other side of the RL goes to ground, right? So basically everything flipped, right? You take this guy and flip it, right? So whatever goes in the is on the up comes down, and vice versa, right? And you have to take care which is the source, which is the ground. What should we do? Where should we apply the VGS? The VGS is applied between the gate and the source in case of a NMOS. Similarly, the VGS has to be applied between the source and the gate. And how did we apply that? We can apply it like this, or we can apply it. In this case, what did we do? What were the ways of applying? The very basic thing that we started off with was this. This is R1, this is R2, this was VGQ. Similarly, in this case, we'll have to do, so this will be R2. If we have to keep the same VSG and same overdrive and so on, this will be R1, because ultimately the voltage across R2 is VGQ. We wanted the voltage across R2 to be VSGQ, right? So VSGQ. How were we applying the input? We were applying the input by AC coupling it into our configuration. So in this case, what should I do? I can AC couple the input as well. Because this is AC coupled, it doesn't really matter whether the VI is reference to a VDD or VI is reference to ground, right? So this becomes the equivalent of the common source amplifier in case of with a PMOS, right? What will be, for example, a common drain amplifier? In case of an NMOS, what was the common drain amplifier? In case of an NMOS, our common drain amplifier was this. I'm not showing the input side biasing anymore. Right, we were taking the output here. So what will be the common drain amplifier in case of with a PMOS? Right, basically the same thing, but everything flipped. So instead of this transistor, instead of the NMOS, we put the PMOS. The drain of the NMOS is connected to the VDD. Here the drain of the PMOS will go to the ground. Correct. Gate is biased again. So you can bias it in any of your favorite ways. I am showing the easiest way to bias. Obviously we know by now that this cannot be done. We need other ways of biasing. What is connected to the source here? What is connected to the source? Feeding current out of the source, right? So in this case, in case of a PMOS, we have to feed current into the source, right? Okay, so we can do that. So we can feed current into the source. This becomes I0, and we were taking the output from the source of the MOSFET, AC couple RL, right? See, right? Similarly, you can sketch the common gate amplifier, right? And similarly, you can do current mirrors, right? We already did a current mirror biasing here. We did a current mirror biasing here with the PMOS. Similarly, you can do cascaded current mirror biasing. You can do wide swing current mirror biasing, right? So what I'm trying to get at here is that whatever you can do with an NMOS, you can do with the PMOS. So you should get used to handling a circuit independently from scratch, even if I am giving you a PMOS, right? Okay. In this upcoming assignment, you will see PMOS circuits. The same known circuits which we have gotten accustomed to using an NMOS. You will see the same circuits using a PMOS. And also for those of you who will be taking the final exam of this course, a spoiler is there will be questions on NMOS, on PMOS and NMOS both. So it makes sense to get yourself accustomed to the circuits using PMOS, right? Okay. I'll see you in the next lecture.